Okay, so I'm gonna go ahead and share my PowerPoint screen with you guys. Okay, so module 3 again has two parts. The first part is acids and bases. The second part is organic reactions. It's not covering the reactions specifically. What it's going to teach you is that there are patterns that you can learn to recognize. And I did include something kind of like that in this slideshow, but it's very different from what is on Top Hat. So that's why, again, that section is for review. So we're going to review the different types of acids and bases real fast. First, we have Bronsted-Lowry acids and bases. Does anybody remember what is being moved around in a Bronsted-Lowry acid-base reaction?
Proton.
Yeah, this is all about protons. So a Bronsted-Lowry acid donates or loses a proton. So this is like when you think of hydrochloric acid, sulfuric acid, you think of them as proton donors. And then what is a Bronsted-Lowry base?
It accepts a proton?
Right. So a base accepts a proton. In organic chemistry, what you're going to see is that the chemistry actually kind of starts with the base. And so we use a lot of terminology like steals or attacks, which always sounds kind of silly, but it is actually the correct terminology. So the Bronsted-Lowry base is going to be the like active species in an organic reaction. So for example, we have water and hydrochloric acid. What is going to be formed in this reaction? Okay, let's start simpler. Which species is the acid?
The hydrogen chloride?
Right, so the hydrochloric acid is our acid. And when it reacts with water, what is it going to form on the other side of the reaction?
Chlorine and
Hydroxide? No, not
Not
hydroxide.
hydroxide, the other charged species of water. What do you call protonated water?
Hydrogen chloride.
Hydronium.
Hydronium, right. So the hydrochloric acid is our acid. It's a proton donor. And the water is our base. It's going to be a proton acceptor. And what that's going to look like with your reaction arrows is the lone pair on the water is going to attack the proton. And then what other arrow do we have to draw? If we just attack the proton, we're going to end up with a bond from water to the hydrogen.
Take the bond away from the hydrogen and chlorine.
Right. So we want to break the bond between hydrogen and chlorine and give the electrons to chlorine. So what that gives us is H3O plus, hydronium, and chloride minus. So this proton here, those two electrons, is the lone pair that did the attacking. And then chlorine has two extra electrons. That came from the covalent bond between hydrogen and chlorine. So hydronium is the conjugate acid of water. Chloride is the conjugate base of hydrogen chloride or hydrochloric acid. So remember, the conjugate acid is always one proton more than your original base, and the conjugate base is one proton less than the acid that you started off with. Okay, another one. We have acetic acid, which is one of your compounds that you need to memorize. And we have ammonia. Which one of these is going to be our acid?
The acetic acid.
Right, yeah. It's not a trick question, right? The one that has acid in the name is definitely the acid. Oh, I gave away the arrow. And then ammonia is going to be the base. And remember, the acid is a proton donor. The base is a proton acceptor or thief. So the lone pair on the ammonia is going to attack the acidic proton on acetic acid, and then we break the bond from the hydrogen and give the electrons to the oxygen. So our acetic acid and ammonia get turned into these products. So remember, this lone pair here is now being represented in this covalent bond. And then the extra lone pair that we have over here came from the covalent bond between oxygen and hydrogen. And we end up with acetate and ammonium. Does this make sense so far? I also want to point out that even though we're talking about protons, what is actually moving in this reaction? Electrons, right. So that's going to end up falling under the Lewis acid, Lewis base definition, which we're going to learn actually encompasses all of our Lewis acid or all of our acid base reactions. Because even though what we're seeing is overall a net shift of a proton, the proton is not the thing doing the chemistry, right? The electrons are the species that actually moved and initiated the reaction. And that's really, really important to know for organic chemistry. Okay, so strong acids. What is the like definition of a strong acid? Do you remember?
It completely disassociates.
Yeah, exactly. Strong acids ionize completely in solution. So they ionize or dissociate. Dissociate goes more with ionic compounds. Since these are covalent compounds, we're going to use the term ionize. So we have 7 strong acids that you're responsible for remembering. So you want these stuck in your head forever. What's the name of this one? HCl?
Hydrochloric acid.
Right. What's this one?
Hydrobromic acid.
Right. Do you guys remember the other 5 strong acids? Just shout out a strong acid.
Hydrofluoric acid.
Hydrofluoric is actually the only halogen acid that is not a strong acid.
Sulfuric acid.
Sulfuric acid is 1.
Nitric acid.
Nitric. Which halogen are we missing?
Iodine.
Right, so hydroiodic acid. And then there's 2 more.
Perchloric.
Yeah, I couldn't tell if you said chloric or perchloric, but both of them are strong acids. So here are our 7 strong acids. And I'll provide this slideshow when we're done here. Okay, so next we want to talk about acids and bases in water. There's a definition that is specific to acids and bases in water, and it's the Arrhenius acid-base definition. We're not really going to use that definition so much because it's so specific, but it is important to remember a couple things about acids and water. So first of all, remember that hydronium is the strongest acid that can exist in water. What that means is that if you put in a strong acid, so one of those 7 that we just looked at, and you put it into water, it immediately forms H3O+. So hydrochloric acid, sulfuric acid, nitric acid, they do not exist in water. What you end up with is hydronium with a chloride counterion, or hydronium with a nitrate counter ion. They immediately ionize and make hydronium. Similarly, hydroxide is the strongest base that can exist in water. So most of our bases that we know of are hydroxide based, like sodium hydroxide, potassium hydroxide, magnesium hydroxide. You know, all these have hydroxide in the name, but there are other strong acids, or sorry, strong bases like ammonia or hydride. If you put those into water, they do create hydroxide. So hydroxide is the strongest base that can exist in water. Does this make sense? I hope so. It's from Gen Chem. Okay, so we're gonna look at a reaction. If we combine hydrochloric acid and sodium hydroxide, we end up making water and sodium chloride. So what we're saying is you take a really strong acid and a really strong base and you end up with salt water, which definitely makes a lot of sense, I guess. Let's talk about the ionic reaction that's happening here. How do we create the ionic reaction?
You separate each molecule into its subsequent atoms.
Right. Yeah, exactly. So you want to break it up into the ions. Before we do that, we have to remember that this is an aqueous solution. So we're not going to have H plus and chloride minus. What we're going to have is hydronium and chloride minus as our active species for the hydrochloric acid. And then we're going to have sodium plus and hydroxide minus. And that's going to give us 2 equivalents of water and sodium chloride on the other side. Before we go to the net ionic reaction, we have to identify our spectator ions. What is a spectator ion?
Isn't it the one that's I know it's both sides. I'm trying to remember though.
Yeah, no, you're right.
Basically, it's only involved in one of the intermediary steps, and after that, it's just kind of goes back to the form it entered in.
Yeah, so anything that is not changed through the reaction is considered a spectator. So in this case, we have chloride on the left-hand side, and we see it on the right-hand side, sodium and sodium. So these are our spectator ions. And so we're going to remove them to get our net ionic reaction, which is H3O plus hydroxide gives us 2 equivalents of water. Oops, I lost my lone pairs here too. Since I typed out these reactions in PowerPoint, I had to doodle in lone pairs. And it was an agonizing like 5 minutes of me trying to make perfect circles. It didn't work out, but that's what you get there. Oh, hey, look, the lone pair showed up. Sometimes I do things correctly. Okay. So all strong acid, strong base reactions have the same net ionic reaction. So if you mix any strong acid with any strong base, you're going to end up with this net ionic equation. So if we had started with sulfuric and potassium hydroxide, we would end up with potassium and sulfate that we would have to remove from the reaction. But we would still end up with hydronium, and hydroxide gives us water. We just might end up with some different coefficients. But it would still be the same species. Okay, so our next type of acid and base to talk about is the Lewis acid and base. And what we're going to start to realize, hopefully, is that Lewis acid and bases cover everything. Everything in chemistry is a Lewis acid base reaction. So even when it doesn't involve protons. And that's because Lewis acids and bases, it's a much broader explanation of acid-base chemistry because it watches the flow of electrons and not protons. So in a Lewis acid-base definition, the acids are electron pair acceptors, meaning they are electron deficient. So they may have a positive charge or a partial positive, such as a proton. Bases are electron pair donors. They are electron dense. And this will include or like encompass Bronsted-Lowry acid-base reactions. So for example, if we have ammonia and hydrochloric acid, we'll end up with ammonium and chloride, right? This is very similar to a reaction that we looked at earlier. So what's happening here is we are moving a proton so that it ends up on the ammonia. But in order to do that, the ammonia, which is our Lewis base, is going to donate its electrons to create a bond to the hydrogen that makes it an electron pair donor. The acid is accepting that pair of electrons. So even though we are overall seeing a shift of protons, it's still an electron-based reaction. So we can also see reactions that have nothing to do with protons. Sorry, I'm turning off my little fan over here because it's making cold. So these reactions are electron-based but have nothing to do with proton transfer. So just looking at these, we have ammonia and we have aluminum chloride. Which species is going to be our base?
The ammonium chloride.
No, it's actually still going to be our ammonia. Sometimes you're going to see things that you haven't seen before, and so what you want to do is try and figure out, what can I know about this compound? So when we're looking at this aluminum chloride, what can we say about this molecule?
It has a 0 charge. Or
Yeah,
no?
overall it has a charge of 0. It's neutral. Do we have any polar bonds here?
No.
Are you sure? We have aluminum, it's a metal, and we have chlorine, which is an electronegative non-metal.
Yeah, but aren't they balanced by the structure of the?
Okay, no, you're right. The molecule itself is not polar, but the question was, do we have polar bonds? So we do have polar bonds here. We're going to have dipoles pointing towards the chloride, which means our aluminum is going to be partially positive, and our chlorides will all be partially negative. And then we have this lone pair on the nitrogen. So you could see why this lone pair on the nitrogen might actually be interested in attacking the aluminum, right? We have something that's partially negative and we have something that's partially positive. And so what we end up with is a complex between the aluminum chloride and ammonia, where we now have a positive charge on ammonia because the ammonia donated its electron pair, which makes it a Lewis base, and the aluminum accepted it, which makes it an acid, and also puts a negative charge on the aluminum. So this is a Lewis acid base reaction, and we're going to see a lot of these in this chapter. Are there any questions so far? Cool. So next, we need to talk about the strength of Bronsted-Lowry acids and bases, and this brings us to pKa. And I know that when we hear the term Ka, a lot of us get like Gen Chem 2 flashbacks. We're not going to do math in organic chemistry. There's no math in organic 1 or 2. What we are going to have to do is remember how these things are calculated, though, so that we can understand what these numbers mean. And then you will just be given the numbers. So how do we quantify the strength of an acid? In chemistry, chemists use pKa to talk about the strength of an acid. So we have to remember where this number comes from. So if you want to calculate any value of K, like a KEQ, it's always going to be the concentration of the products over the concentrations of the reactants. And there may be some exponents involved depending on coefficients in your reaction. But for a general acid-base reaction of HA plus water producing hydronium and A minus, your Ka reaction looks like this, where you have the concentration of hydronium times the concentration of your conjugate base over your acid. And then to calculate pK, we take the negative log of Ka. So remember that P, the little p, always means negative log of. So when you see pH, that means negative log of the concentration of hydronium. Okay, so for a strong acid, if an acid is strong, which side of the reaction are we favoring? Are we going to see more A minus or HA in solution for a strong acid?
Reactants.
Yeah, we're going to see mostly hydronium and A minus. So A minus is going to be a much greater concentration than HA. So these numbers are going to be large, and this number is going to be small. What is the value of Ka going to be? Is it going to be a big number or a tiny number? If we're dividing two big numbers by a tiny number.
Big.
Yeah, it's going to be a huge number, potentially. It's going to be greater than 1, possibly much, much, much greater. And if it's a strong acid, like a very strong acid, it will be much, much, much bigger. This means that pKa will be very small, because when you take the negative log, you're essentially getting the inverse of the exponent. So if your Ka is something like 10 to the 5th, because it is a very strong acid, your pKa would be -5. And this is why we like to use pKa, is because there's no decimal places really. Like if you have a really tiny number, you're not looking at 0.00000001. You're looking at just a single number to compare. So your pKa would be -5. So when you think of strong acid, think of very low pKa. For a weak acid, which species will be prevalent? Will we see more HA or A minus?
HA.
Okay.
Yeah, we're gonna see a lot more HA. So this number could potentially be a lot larger than the number on top. So is the value of Ka going to be large or small?
Small.
Yeah, it's going to be small. It's going to be something 10 to the negative x, right? Let's say it's 10 to the -7 for, no. Yeah, -7 is fine. And let's go bigger. 10 to the -20. It's going to be a small number. That means that pK will be large. If you take the negative log of 10 to the -20th, what will your pKa be? So if the pK of 10 to the 5th was -5,
20.
20. Right. So what we want to start getting in our heads is that if we have a small number, we are looking at something that's more acidic. If we have a larger number, we're looking at something that's more basic, potentially.
Can you say that again?
Yes, I'm going to say it about 100 times in this chapter as well. So when we see a small number, we want to think about something that's more acidic. And when we see a big number, we want to think about something that's more basic. And always, pK will always be a comparison situation. So we'll have two compounds we're looking at. One is -5 and one is 20. You want to know what the stronger base is. It's negative, or sorry, stronger acid. It's -5. Okay. So we're going to look at the pKa values of some common compounds. I put them all here in the column for you. It should also be there. Actually, maybe I deleted them in the version that I gave you guys so that you'd have to write them out. There are a couple here that I want you to memorize. Remember that anytime I put an asterisk next to something, that's my way of saying I need you to know that. You are going to end up memorizing a lot of pKs for OCHEM. So this is another thing that you should just go ahead and start flashcarding. So hydroiodic acid is an incredibly strong acid. It has a pK of -10, which means its Ka is 10 to the 10th. So there's a lot more hydronium and iodide in that solution. The pKa of hydronium is -1.74, which means anything that has a pK larger than that is not a strong acid. But notice we also have like acetic acid here at a pK of 4.76. What you're going to learn is that most carboxylic acids tend to be in that area, somewhere between 3 and 5. And then we have ammonium at 9.2. Water is another one to have in your head as like our neutral point is 15.7. Ethanol is at 15.9. And then we have our alkynes. And I know we don't usually think of alkynes or like carbon compounds as being acids. We're not really talking about them being acids here. We are talking about how easy it is to remove a hydrogen from that compound. So for an alkyne, the pK is 25. Ammonia is 38. Alkenes, 44. Alkanes, 50. And we're going to talk about why that is in a little bit. So as you're looking at this chart, your increasing acid strength is going up, right? So here are your stronger acids, and here are your not acids, right? So then if we look at our list of conjugate bases over here, which conjugate base is stronger, iodide or the conjugate base of ethane? Does anybody remember what the relationship is?
Isn't it the opposite?
Ethane
of
conjugate.
iodide?
Right, it's the exact opposite. So if something is really, really good at being an acid, that means it's a fantastic proton donor. In order for it to be good at that, the conjugate base has to be happy on its own, which means it's going to be a weak base. It's not going to be able to take the proton back. If it could, this would not be a strong acid. The alkane, however, is a very crappy acid. So if you manage to remove that proton that does not want to be removed, you're going to end up making something that's very unstable and is going to steal the first proton it sees. That makes it a very strong base. So the stronger the acid, the weaker the conjugate base. That's kind of the general rule here. So again, for example, if you have, if you're trying to compare bases, the easiest way to compare bases is actually to look at their conjugate acids. So then you only have to have one set of numbers in your head. So if you can see the pK of some of these, like the pK of hydrochloric acid is -7, the pK of acetic acid is 4.76, the pK of water is 15.7. That means that you can organize their bases based on that. So the strongest acid will have the weakest base, the weakest conjugate base. The weakest acid will have the strongest conjugate base. So I'm going to say that part again. The strongest acid will have the weakest base. The weakest acid will have the strongest base. Does that make sense?
Yes, ma'am.
Cool. I used to do these notes handwritten for my class, and I actually think that this slideshow is much clearer. So I'm glad that I took the time to make this. Okay, so acid-base equilibrium. This is the situation that I don't think you do this a lot in Gen Chem, but we're going to look at some reactions and we're going to try to predict which side of the reaction is favored. So if we react ethanol with hydroxide, what will our products be? Which compound is our base, first of all?
Wouldn't it be the OH?
Right. So if you're not sure, the thing that is most negative has the most electrons. It tends to be your base. So hydroxide is our base. That means that it's going to be an electron donor. Where are its electrons going to go? If I were to draw an arrow from here, where am I going to draw it to?
The H?
Right. Okay, and then what other arrow do I need to draw?
Breaking the bond from the oxygen and hydrogen.
Right. So I'm going to take these 2 electrons and put it back onto oxygen. And I don't think I drew the products. No, I didn't. Okay. So that's going to give us the conjugate base of ethanol, which is ethoxide. And what's our other product?
Water?
Yeah, it's water. Okay, so if we want to figure out which way this reaction goes, we need to compare the pKa's of the acids here. So does anybody remember from the previous slide what the pKa of the acidic proton on ethanol is?
So negative 0.4 something.
No, it's 15.9. That's kind of a mean question to ask you guys since I just showed them to you the other day, like a minute ago. What's the pKa of the one of the protons on water?
15.7.
Mm-hmm. Okay. So between ethanol and water, which acid is weaker?
Ethanol.
Yeah, ethanol is our weaker acid. So which side of this equilibrium is favored?
The right side?
Well, so we favor the weaker acid, and we said that ethanol is the weaker acid. So we're going to favor the reactants. Based on the difference between the 2 pKa's, is this going to be like there's only ethanol present reaction, or do you think it's going to be largely in equilibrium?
Probably equilibrium because they're so close.
Yeah, I would say like if there's even really a difference, there's maybe a little more ethanol. So the next one is a little trickier. I'm going to give you the pK of phenol. This is another one that I want you to memorize. So 9.95 for the pK of phenol. And then on the other side, we're going to have the same reaction happening here. We're just deprotonating an alcohol functional group. Also, I took the time to write these out during class because drawing organic structures is really important. When you get to OChem 2, you're more likely to have to submit some of your work in class. You will have to draw structures all the time. So just because our class is online doesn't mean that you shouldn't be practicing drawing structures. Okay, so here are our 2 pKa's again. If we're comparing 9.95 and 15.7, which acid is the weaker one? Is it phenol or water?
Phenol? No. Water.
It's the water, right? So remember, we're looking for the bigger number. If we're looking for which one is the weaker acid, we're looking for the bigger number. So which side of the reaction is going to be favored?
The right.
Right. And this one actually will be fairly significant. So typically the difference between them can kind of give you a ratio on a logarithmic scale. So this is about 16 over here, and this is about 10. The difference between those is 6. So there's probably about 10 to the 6th more of these products than what we have over here. I'm never going to ask you to do that, but I'm explaining a little bit about why these pKa values matter. Okay, next one. This is a thing that we have not seen yet. So this right here, do you remember when I told you guys about amides? I said that there's another thing called AMIDE, and it's pronounced amide. That's what's happening here. So an amide is a negatively charged amine. So that long I sound is a compound like this. So between the alkyne and the amide, which one looks more like a base to us?
The alkyne.
Well, so remember that a base is an electron donor and an acid is an electron acceptor. Does this nitrogen look like it wants any more electrons?
No.
No, it has too many and it desperately wants to get rid of them, right? So where are we going to draw our arrow to?
The hydrogen.
Mm-hmm. And we'll put the electrons onto the carbon. Okay, so this gives us a carbanion, which is a negative charge on a carbon. This type of anion is called an alkanide. And then what's our other product here? If we take NH2 and add 1 hydrogen, what do we get?
NH3.
Mm-hmm. Okay, so on the left-hand side, the alkyne acted as our acid, so we need to know the pKa of this. What is the pKa of an alkyne?
$25.
There you go. Good job. 25. What's the pKa of ammonia, which is our conjugate acid over here? So we had our base and it makes the conjugate acid. So we need to know the pKa of this guy.
38.
38. Which one is the weaker acid?
NH3.
Right. So then which side of the reaction do we favor?
The right.
Mm-hmm. Yeah, and this is a significant difference, right? There's a difference of 13 between the pKa's. So there's 10 to the 13th more of the right-hand side. Okay, does this make sense? So what you're always doing is comparing the pKa of the acid from the left-hand side to the pKa of the conjugate acid that was formed on the right-hand side. Okay, so this brings us to the relationship between structure and acidity, because these numbers, they're not arbitrary, right? Like these differences in acidity have to come from somewhere. So, and a lot of times you guys are gonna be given compounds where you don't have the pKa value memorized, but you can compare it to other compounds that you do know, and you can compare the structures of several molecules. in order to give you like an estimate of the relative acidity. So the 4 main contributors to acidity are electronegativity, hybridization of the atom that the hydrogen is attached to, resonance, and the inductive effect. And I have a slide for each one of these. Some of them have multiple slides. The really, really big thing to know before we go anywhere is that the acidity of a compound is directly related to the stability of the conjugate base. The more stable the conjugate base, the more acidic the acid. So let's just think about this for a second. Say that you're looking at hydroiodic acid. It's very, very acidic. So what that means is that it is more happy existing as H plus and iodide than as HI. So that means that the conjugate base, iodide, has to be very, very stable in order for it to be happier separated from the proton, right? So then if you have something that's not very acidic, say ammonia, which has a pK of 38, that means that that compound is happier existing as NH3 than as NH2 minus and H plus. And the reason why is that NH2 minus is incredibly unstable. It is very, very reactive. So the more stable our conjugate base is, the more acidic the acid will be because it'll be more comfortable separated from its proton. So what we're looking at in all of these factors here is these all somehow stabilize the conjugate base. They all contribute to the relative stability of the conjugate base and the weakening of the bond between the base and the proton. So our first trend is electronegativity, and this one's kind of bizarre. First of all, this only matters when you're looking at compounds that contain only 2 elements. So methane only has carbon and hydrogen. Ammonia only has nitrogen and hydrogen. Water only has oxygen and hydrogen. So these are all compounds that only have 2 atoms here. And then I've arranged them in the order of the periodic table. So as you go from left to right across a period, so in a single row, that's the only way that you can do this comparison. You have to stay in a single row or a single column. Acidity will increase as electronegativity increases. The reason why is that you are creating a more polarized bond. So the difference between carbon and hydrogen is very slim. So maybe you have a little tiny negative, a little tiny positive. If that bond isn't very polarized, that means that they're sharing the electrons pretty evenly. That proton is not going to act like a proton. Another base is not going to be able to pull off a very slightly positive hydrogen. But by the time you get over to hydrofluoric acid, even though it's not one of our strong acids, it's still an acid. I mean, look at the pK, it's 3.2. This has a giant negative on the fluorine because fluorine is our most electronegative atom. This is a giant positive. This is as close as you can get to like a nearly ionic compound. You know, all these acids here, they're practically ionic, but they are not. So the more positive that hydrogen is, the better off it's going to be as a proton. And the more electronegative this atom is, the happier it's going to be existing as its anion. So that's our trend from left to right. As we go down the group, so again, staying in a column, we have 2 things that are happening here. The electronegativity is decreasing, but the acidity is increasing. So a second ago, we saw increase in electronegativity increases acidity. But as we're going down, the decrease in electronegativity increases acidity. So it's not the electronegativity that's really acting here. What's happening is we're comparing the atomic radius. So as we go down the group, what is happening to the atomic radius? Is it getting bigger or smaller?
Bigger.
Bigger.
Yeah, it's getting much bigger. And so you need to think about the attraction between the proton and the, what am I trying to say? The proton and the conjugate base. So think about fluoride for a second. You take away the proton and you have fluoride. Fluoride is a teeny tiny, very compact atom, and it has this one single negative charge that is spread across its surface. It's going to be fairly concentrated though, because it doesn't have a lot of surface area. But then you get to iodide. Iodide is this huge atom, and it still only has that one single negative charge across that entire electron cloud. So which one of those species is the H plus going to be more attracted to? The teeny tiny, very compact and concentrated negative charge, or the negative charge that is spread across a giant surface? So the tiny compact negative or the spread out negative? Which one does the H plus like more?
The spread out.
It's actually the opposite. So since this charge is so spread out, the H plus like can't even find that negative charge across the surface. But fluoride is so tiny, its negative charge is much more prominent. And so the H plus likes that a bit more. So that's why hydroiodic acid is so much more acidic than hydrofluoric acid, even though the electronegativity has decreased significantly. And so the polarization of this bond has decreased significantly. The increase in atomic radius makes it more acidic. And that's true down any group. So sulfur is below water. So hydrogen sulfide is more acidic than water because it's below it. Does that make sense? Yeah, and then phosphorus is below nitrogen. So if you're trying to pull off a hydrogen, it's going to be more acidic. And you can do this across other periods as well. So going this way, you would have phosphorus, sulfur. This would be silicone. We don't really use silicone. Just going across, you would see an increase in acidity. So overall, our acidity increase is this way across the periodic table. Do these trends make sense? Okay. And again, this only applies for these situations. So only when you're talking about methane, ammonia, water, hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic. That's how we explain these trends. But then when you get to larger compounds, you have to think about other factors. So hybridization of, I forgot to animate this slide. So there's a lot of information all at once. For these compounds, it's the hybridization of the carbon atom that contributes to the acidity. So remember that s orbital electrons are lower energy than p orbitals because they are held closer to the nucleus. If something is more stable, that makes it, or sorry, if something is lower energy, that makes it more stable. So the carbons that have more s character are going to be able to stabilize a negative charge more easily than a carbon that has more p character. So the carbon in the alkyne is sp hybridized. So if we deprotonate it and create a negative charge on carbon, that negative charge is sitting in a much lower energy orbital. So this is more stable. If we deprotonate the alkane, we're deprotonating an sp3 carbon. This is sitting in a much higher energy orbital, so it's going to be less stable. So the more stable the conjugate base, the more acidic the acid. So the alkyne is going to be the most acidic because its base is the weakest base. But then the alkane is the least acidic because its base is really unstable. So you're not going to be able to form it as easily. Does this relationship make sense? I haven't gotten any questions in a while, so I just want to check in with you guys. I'm clicking.
This
through.
one's harder for me. I think it'll just take some reading and review though.
Okay. Yeah, and this one, this isn't one that you have to worry about as much as far as comparing compounds. I'm perfectly happy with you guys memorizing, these pKa values. If you have these, I'm great. If you don't remember exactly why, that's not really something I'm going to test you over directly. The next two things are ones that you get tested over more. But yeah, this line tells you what you need to know. Okay, so our next one is the effect of resonance on acidity. And I forgot to animate this one as well. So resonance is stabilizing for a molecule because you're delocalizing the negative charge. Remember that no single atom wants to carry the load of a negative charge on its own. Even if it's oxygen, which is very electronegative, it still does not want to be holding that charge on its own. It's much easier if it can share it with a friend. So the pKa of acetic acid is one that we're working on memorizing, right? It's 4.76. If you put it into water, it will dissociate a little bit, and you will end up with a small amount of acetate and hydronium. The acetate ion is resonance stabilized, so we can move these electrons to create a double bond. We can take these pi electrons and push them up onto the oxygen. And so that's where we get that other lone pair. And then we took one of the original lone pairs and made the pi bond. So being able to stabilize that conjugate base makes carboxylic acids a little more acidic. Whereas if you look at ethanol, which has the same number of carbons, but it does not have the double bonded oxygen, the pKa is 16. And the reason why is that if we were to deprotonate this, we're stuck with ethoxide, which does not have any resonance. It has nothing to stabilize that. So the only reason that ethanol is even acidic at all is because this bond is polarized. So again, this can be summarized by the more stable the conjugate base, the more acidic the acid. Oh, we're getting a new refrigerator today, so if you hear the doorbell and stuff, our refrigerator broke, so we're excited. Okay, so does this make sense? The more stable the base, the more acidic the acid. So resonance is stabilizing. Okay, our next idea is the inductive effect. And I think this is probably a newer word for us. So induction is referring to the tendency of electronegative atoms to draw electron density towards themselves, which ultimately weakens the bond of the proton to the conjugate base. So this is one of the effects that it actually has several different things happening here. So one, it's weakening the bond of the proton to the conjugate base, but also this induction we're going to see stabilizes the conjugate base. So for example, we're going to compare acetic acid and ethanol again. We're going to look at the dipoles. Okay, sorry. I was checking on my fridge situation. The dipoles that are created. Okay, sorry, my computer is telling me it's about to die. That's what I get for running a USB powered fan. Okay. So if we look at the dipoles across these molecules, we can see how they affect the pKa of the hydrogen. This hydrogen on the acetic acid is going to be a little more positively charged because we have a dipole pulling electron density away from it this way. But then we also have the carbonyl pulling electron density towards itself. Remember, there's also a resonance form here. It's not super great to do this because we're going to end up with a separation of charge, but there is a resonance form that we could look at. Oops. That shows how the negative charge can be held on the oxygen. So that's part of the inductive effect here. The electronegative atoms that are on the other parts of the molecule are pulling electron density towards themselves, which weakens the bond of the proton. In the resonance form that I just drew and then erased, we saw that this can somehow put a partial positive onto this oxygen. Is H plus going to be as interested in a bond to an oxygen that has less electron density?
No.
No, because remember, chemistry is all about opposites attract, and things that are the same are going to repel. So this H plus is going to be less interested in that oxygen because some of the electron density is pulled onto this oxygen, which means this bond is weakened, and therefore the H plus is more free to go. When you look at ethanol, there's only one dipole happening here. So this hydrogen is pretty well stuck onto this oxygen because the entire density of electrons is on this one oxygen. So this hydrogen is very happy with its situation. That bond is less likely to be broken. So weakening the bond of the proton allows it to be extracted more easily. And that's the first bit of the inductive effect. We're going to look at another version of this in a second. Are there any questions about this so far? We feel pretty good? Okay. So the next thing that you can have an inductive effect for is if you have electronegative substituents on a molecule. So we're going to look at acetic acid again. What is the pK of acetic acid? We've seen it maybe like 5 or 6 times already today.
Is it 4.7?
Yep, 4.76. We're going to compare that to different versions of acetic acid. We're going to add on fluorine groups. So we're going to add on 1, 2, and then 3. So let's think about what's going to happen here. We have just regular acetic acid, which has a pKa of 4.76. If we put on an electronegative fluorine, how is that going to affect the dipole? We have a dipole here. But as far as this part of the molecule is concerned, electron density is going this way as well. So we're focusing electron density right here. What is the fluorine going to do?
It's going to turn that more toward the fluorines.
Right. So this part of the dipole is no longer going to exist. We're still going to have electron density essentially this way, right? Like it's all going to be focused over here. And when we do that, we're starting to pull electron density away from this bond a little bit. So we are weakening the OH bond. Is that going to increase or decrease the acidity of this compound?
Increase?
Yeah, that's going to make this compound more acidic. So the pK of fluoroacetic acid is 2.59. So then if we have 2 fluorines, at this point we have 2 fluorines, which are more electronegative than 2 oxygens. We have kind of started to flip this dipole. The electron density is going to be more focused on this end. So we've even further weakened this bond. So we're going to become even more acidic. our pKa is 1.34. And then by the time you get to trifluoroacetic acid, which is often called TFA, it's a very common acid in some organic syntheses, your pK ends up being 0.23. So still not as acidic as some of your very strong acids, but it will still burn your skin. We used to use this in my lab in grad school, and fortunately I never had to use it for any of my reactions, but some of my lab mates had really horrible like burn scars on their arms from the TFA splashing at them. And when TFA hits your skin, it leaves a little like black burn that takes a long time to go away. It's a pretty scary little acid. So the dispersal of charge is going to stabilize the conjugate base, and also the withdrawal of electron density from the OH bond is going to weaken the OH bond. So that's the other thing that I didn't quite talk about is in our conjugate base of TFA, not only is it resonance stabilized with the carbonyl, but since we have a dipole that is fully flipped this way towards the 3 fluorines, the electron density is not living on this oxygen. It is very well spread out across this entire molecule versus acetic acid. It has a conjugate base, acetate. The negative charge is spread between the 2 oxygens, but that's it. Here, we're going to see the negative charge spread out more or less across the entire electron cloud. So that's going to stabilize that conjugate base. Does this make sense so far? Okay. Our next topic is phenols as acids. So we're going to compare cyclohexanol to phenol because they have the same number of carbons and even kind of the same shape. Not really. What we're going to learn later is that benzene is flat and cyclohexane is definitely not, but it kind of looks the same to us. So the pKa of cyclohexanol is really close to any other alcohol. It's a little more basic than ethanol. It has a pKa of about 18. And the pK of phenol, we learned earlier, is, I said 9.95 earlier. This value is a little different. Let's go 9.9 is fine. So 9.89, phenol is significantly more acidic than cyclohexanol. The reason why is that the benzene ring is electron withdrawing. So this is an inductive effect happening. We're pulling electron density away from the oxygen. And also phenol and phenoxide are resonance stabilized. So if you deprotonate phenol to create phenoxide, you can move the negative charge around the ring in a lot of different ways. You can create quite a few resonance forms. So we'd have a negative charge here on this carbon and a double bond here. And you could continue to move it around. And so you could get several resonance forms by doing that. So that one's going to be a lot more stabilized than cyclohexanol, where once you deprotonate it, that's it. There's no resonance form. Okay, so we're going to do a couple practice problems here. So we're going to predict the products and the direction of equilibrium. So we have sodium hydroxide and phenol. What's going to happen in this reaction? Which compound is our base?
Sodium hydroxide.
Right. So remember that sodium hydroxide, it would dissociate to sodium plus and hydroxide minus, and that negative charge gives us a pretty solid hint that that's our base. So then what is the base going to do?
It's going to attack the hydrogen on phenol.
Right. And then we're going to have to break the bond between the oxygen and hydrogen. And that's going to give us phenoxide. And what would our other product be?
Water.
Right. Okay, so if we want to predict the direction of equilibrium, we need the pKa of our acids. So what was the acid in the reactant side?
Phenol.
Phenol, which has a pKa of around 9.9. I learned 9.95, so I tend to write that one out. What is the acid on the product side?
Water.
Right, so water is the conjugate acid of the base. And what is the pKa of water?
$15.7.
Right. Okay, so which acid is weaker, phenol or water?
Water.
Water. So which side of the reaction do we favor?
Products.
Right. Remember, we favor the weaker acid, the larger number. So this reaction is going forward. Okay, in our next one, we have a very similar setup, right? We have an alcohol and we have hydroxide. I'm not going to make you fill in all the blanks again. That's going to give us a conjugate base. And our other product will be water again. And we know that the pKa of water is 15.7, and I give you a pKa of about 18 over here. So which acid is weaker, our hexanol or water?
Hexanol.
Right, so then which side of the reaction do we favor, the reactants or the products?
Reactants.
Reactants.
Right. And which equilibrium is less of an equilibrium? Does that question make sense?
The top one.
Right. Yeah. So the difference in pKa is much greater in the top reaction. So this one is going to be a much more significant preference than the one below. So there's about 100 times more product over here because 10 to the 2. And over here we have a difference of like 10 to the 6th. So that's a lot. Okay. So our next topic is organic compounds as bases. So far, we've only used like really negatively charged things as bases, and we've seen water used as a base. If we were to react water with a strong acid, what product do we get? Do you remember?
Weak base.
Hydro.
Right, we end up making hydronium, right? So we end up, sorry, that's an arrow, with H3O plus. Your alcohol is going to do the exact same thing because the alcohol is basically water, but with an alkyl group. So it's going to pick up the proton from an acid. And we would end up with a protonated alcohol and our conjugate base. When you protonate an oxygen, it creates what's called an oxonium ion. Okay, what's our next functional group? What's this?
In ether.
Yes, right? It has a carbon on ether side of the oxygen, so we know that it's an ether. It looks like water, again, especially since I drew it the way that I did. It's going to do the same thing. Remember, all the electrons are focused on the oxygen, and you can only start chemistry with electrons. Okay, and then what's this next functional group?
Ketone.
Ketone?
Right. So where are the electrons on this molecule? It's not a trick question.
Oxygen?
Yeah, so it's the ones that I drew out. Are we starting to see a pattern here? Organic chemistry is just a bunch of patterns. If you can learn those patterns, you are set. Okay, and then our bottom one, this one's a little trickier, but we know that HA is shorthand for a strong acid. So that's still going to be our acid. So we have to figure out how this alkene can serve as a base. Where does an alkene carry extra electron density?
In the pi bond.
Right. So remember how I took a lot of time explaining that a pi bond is above and below the sigma bond? So you have your flat alkene, and then your pi density is above and below. The reason why that's important is that these electrons are free to react. Whoops. Hey. So we can protonate an alkene just like we can protonate an alcohol or a ketone because there is electron density in that pi bond. So we're going to redraw our carbon framework here. I'm going to draw the A- off to the side. So when we did this, we took these electrons and we created a bond to hydrogen. So you have to pick a place that was part of that pi bond to put the hydrogen. You could put it on this carbon or this carbon. It wouldn't matter because the alkene was symmetrical. Oh crap. I mean, dang. Sorry. But when we do that, you have to remember that we took away electrons from the other carbon. So that's where the positive charge ends up. Notice how every single one of these reactions, we ended up with overall neutral products, right? Because we had our A- and we have our plus. We have our A-, we have to have a plus. So the electrons from the pi bond are used to make this covalent bond, which means this carbon lost electrons and therefore becomes positive. This species is called a carbocation. And we are going to see these very, very often. They're not ever the final product. They're always an intermediate in a reaction. Oh, I'm so sorry. It's 11:42. I guess I need to let you guys go. Are there any questions about that? Sorry, I'll start setting the time.
TE. Nope.
What?
I don't know what they said.
I
but
think he just
said
was spelling out nope.
Okay. Yeah, so I recorded this lecture. So when we end the class, it'll save it and then I'll upload it. I see a question. Do you have to go to office hours to review the quiz? You should be able to see the correct answers once the quiz is over. If you can't, I'll adjust my settings. But you should be able to see it. And then, yes, you can come to office hours and ask me questions. I have office hours Monday and Tuesday at 1 p.m. and Thursday at 9.
I have a question. So, we didn't like do attendance today. Is the quiz just our attendance?
Right.
Okay, thank you.
Mm-hmm.
Have a great weekend. Thank you.
You too.
Dr. V, you're the best. Peace out, Scout.
Bye.
Thank you.
So I'm trying to look over the quiz, but it's not letting me look at my answer choices or what I did wrong and right. It just gives me the score.
Okay. Let me see what I can figure out. Okay, Top Hat doesn't want to load, probably because recording on Zoom. Oh, here it goes. But usually when I'm doing Zoom and recording, it slows down my computer dramatically. It's kind of loading. I will try to fix these, I guess, when we're done here. Because yeah, it's kind of going slow.
Okay, thank you.
No problem. Any other questions?